So in this video we're going to look at continuity. Now continuity, which is the noun form of continuous, in everyday language it just means unbroken, right? So certain things in the world we imagine to be continuous, like time, for instance. Like time is pretty smooth and continuous. There's no break in time so far as we know. So like for example, a curve that looks unbroken and smooth, not necessarily smooth, but just unbroken, we would say is continuous. And one that has some sort of interruption, which can take a few different forms, as we'll see, would be not continuous. Now the math definition of continuity is actually pretty formal, and that says that if a function f of x is continuous if and only if, that's what those two f's mean, if and only if the limit of f of x as x goes to c is equal to f of c. In other words, the y value that you're approaching as x approaches c is actually the same as the value of the function at that point. And so the example here at the bottom I think is going to help demonstrate that more clearly. If we look at the graph, call this the graph of f of x, we can say that f of x is continuous at -2. So notice that, like, in addition to describing an entire curve as continuous, like this curve up here, we'd say the whole curve is continuous. We can also talk about continuity at a certain point. So like that's what's written here. A function is continuous if it is continuous at every point on its domain. So this function here is continuous. This function here at the bottom in red is definitely not continuous everywhere, but we can talk about it being continuous at certain points. So f of x is continuous at -2. So it's continuous at x equals -2. So that's how we describe continuity at x values. It's continuous at x equals -2, and then your explanation should be just using the definition of continuity. It's continuous because the limit as x goes to -2 of the function, that's equal to f of -2. To see that more clearly, just evaluate them. The limit of f of x as x goes to -2, you can see, it's a little off. It's supposed to be a 1 there. So I'm just going to move this, pretend this is a little bit higher. Or you know what, we'll do this. We could put a 1/2 there. 1/2 is equal to f of -2, which we can see clearly is 1/2. F of x is not continuous. So f of x is not continuous or discontinuous at x equals 4. And the reason is because the limit as x goes to 4 of f of x is not equal to f of 4. So to see this more clearly, just evaluate the limit of f of x as x goes to 4. That is 5. Right? If you go to the graph, you can see that this is 5. But that's not equal to f of 4, which is 7. So even though, like, informally you can see that there's a break in the graph, right? There's a little hole right at 4, 5. That tells you informally, like, oh, it's not continuous there. But your reason should invoke the definition, which is right here. And let's look at that last example. F of x is also discontinuous at x equals 8. And this is because the limit as x goes to 8 of f of x is not equal to f of 8. So how do I know? Well, because the limit of f of x as x goes to 8 does not, is 1. Looks like it's supposed to be a 1. But that's not equal to f of 8, which does not exist, right? There's no value of f of 8. There's no value associated with f of 8. So this bottom part is really like a more thorough explanation as to whether something is continuous or discontinuous. Informally, if I put a picture in front of you, it's pretty easy to see. If you can just trace your finger without ever having to lift, trace the graph without ever having to lift your finger up, then the graph is continuous. If at any point you have to lift your finger up, it's not continuous at that point. But it's not continuous for these reasons here listed below. So on the next page I'm going to show you types of discontinuity. So there are certain sort of categories of discontinuity that we have. So the first type is called a removable discontinuity. And so a removable discontinuity is a discontinuity that can be removed by plugging in a hole. So for instance, we can see that the graph is discontinuous here at A, but it's like fixable, right? If we just kind of took our pen and filled that in, we wouldn't have to really change the function a whole lot to get a continuous graph. I mean, all we'd have to do is fill in that one point. So that's why it's called a removable discontinuity. We're removing the problem by plugging in that hole. Compare that to this one. This is a jump discontinuity. This is not removable. It's not removable because you can see that it's clearly there's a break in the graph. There's no way to fix it. The only way to fix it would be to move this whole right arm down. But as soon as you do that, you're changing the function. Like it's not what it is, it's not exactly what we're looking at now. And you can't do that. You can't just change a function like that. So this is not removable. This is a jump discontinuity, and it can't be fixed. And then lastly, we have an infinite discontinuity, which also is not removable. An infinite discontinuity is often a vertical asymptote. And that is not removable clearly because there's no way to fill out, there's no way to get these two arms to connect without drastically changing the function, and we don't want to do that. So that's also not removable. So our three types of discontinuities are removable, jump, and infinite.